that was smaller than all the other ones. And then you would say, ah, that one must be the minimum. So again, that's not a process that anyone would want to do. So instead, using calculus, what property does the maximum point have, and what property does the minimum point have that gives away the fact that it's either the maximum or the minimum? Yeah, the slope is 0. That's a dead giveaway. That if you're at the tippy top, then your slope right there must be 0, which means your f prime of x, whatever it is, has to equal 0. And then also at the, folks, if this is the tippy top, is that the bitty bottom? Does anyone know? Is there a word for that? I refer to it as the tippy top and the bitty bottom. I don't know about you guys. So at the bitty bottom, you also know that the slope is 0, and so you'd be able to say f prime of x is equal to 0. So to answer this question, how can you find the maximum or minimum of a graph? That might be the first thing that you would want to write down. The max min is found where f prime of x is equal to 0. And conceptually, what that means is you have found a point on the graph where the slope is 0, and if the slope is 0, that means that you've leveled out. So that means it's either at the top or the bottom. Now, here's the question though. Just because the derivative is 0, does that mean that you found a max or a min? Is there a third alternative? Is there some other feature on a graph where it goes flat, but it's not a max or a min? What would that even look like? Your graph went flat, but it's not the bitty bottom or the tippy top. Are there alternatives? You might be thinking, geez, is there another one? There's at least 2 more. There's at least 2 times when a graph has 0 slope, but it's not the tippy tip or bitty bottom. What would it be? Can you imagine anything? You should give everyone blank sheets of paper and crayons and see if you can draw something that eventually looks like it's flat. Well, let's try to figure it out. At the very least, if the slope is 0, I know that it's got to look like that. Well, what could the rest look like? You know, where does the rest of it go? I know that it's got to be flat, at least temporarily. So then what can I draw over here? Line going up. I could draw a line going up, and then over here, what can I draw? If I draw another line going up, then that's a minimum. That's the bitty bottom. But what's another option? I could have drawn a line going down. And in fact, that's the function y equals x cubed. That is what happens. It comes up, levels out, and it goes up. And temporarily, for 1 hot second, what's the slope? 0. So what do we call that then? Is it a maximum? No. Is it a minimum? No. What is it?
Average?
A what, Rosa?
An average?
An average? Yeah, I don't know. I mean, it's not really either. It's not a maximum, it's not a minimum. And yet, nevertheless, f prime of x is equal to 0 at that point. I don't think there's an official name for that. I think sometimes I call it a transitional point. Right? It's coming up, it transitions, and then it keeps going up. You could, the technical name for it is any x value. Let's write that down too. Any x value such that f prime of x is equal to 0 is a critical point. That's what it's called. Critical point. To which I can imagine anyone saying that to their friends, like, oh, that was a critical point you just made. Yeah, so that's a critical point, but it's not a min or a max. Okay, can we draw something else? What else could we possibly draw? All we know for sure is that it has to just go flat. But then what? We've already tried it going up and up. We've tried it going down and down. We've tried it going 1 up, 1 down. What's that, Luis? A parabola would be like this. That'd be a minimum. What's another option? We could just do the opposite of that one, right? And then in that case, I mean, it's kind of the same solution, but you're right, we could do that one as well. So that's not a minimum or a maximum, it's just a critical point. What else could the drawing look like, folks?
Just a line.
Yeah, just a line. Absolutely, right? It could just be flat everywhere. Is that a maximum? Is it a minimum? Is it both simultaneously a maximum and a minimum? Or is it neither a maximum or a minimum? I don't know, but this is still a possibility of the slope being 0. So folks, how many different types of critical points are there? There's 4 types of critical points, right? Critical points. And what are they? Just generally speaking, how and when can a graph have 0 slope? The type 1 would be a maximum. And type 2 would be a minimum. And type 3 would be a transition. I'll just call that transition. And type 4 would be flat. Right? So all of those are called critical points. And so anytime you want to find a critical point on a graph, you just take the derivative, set it equal to 0, and then whatever you solve for x, that will be a critical point where the slope is at least temporarily 0. It could be temporarily 0 at the top, it could be temporarily 0 at the bottom, it could be temporarily 0 as it transitions, and it could actually be permanently 0 if it's a flat function. Now that we've covered 4, is there a 5th? Can you imagine a possible 5th one? I just did. I mean, it's just silly. It's just a combination of these. What's another combination we could do? Could it be flat for a while and then go up? I mean, sure, it's not a function I know of. I don't know what the equation for that function is, but it could go flat for a while and then go down. Right? But technically speaking, that point right there still has 0 slope. Right? So that's what we're looking at. Is we have these things called critical points, and to find them, you just take the derivative, set it equal to 0. So let's try that. And by the way, we just answered this question. How can you find the maximum or the minimum of a graph? So how do you? What do you set equal to 0? The function. Not the function, the derivative. Yeah. How do you find the max or min? You take the derivative and set it equal to 0. So everybody on your line sheet of paper, here's a problem. And it says, if f of x is equal to 4x squared minus 4x plus 2, find the derivative. And then it says, use the derivative to tell me the x value of the minimum of this parabola. So let's go ahead and start just by writing down the function. F of x equals 4x squared minus 4x plus 2. Now, we can all, even without a graphing calculator, imagine what this looks like. What is the shape of this function? It's a what, Anna? It's a parabola facing what? Up or down?
No. No, sorry. Up.
Yeah. So we can just make a quick little sketch. It doesn't have to be perfect. It just, we know it's a parabola, and so we know there's a minimum, and we just want to know where is that minimum? You know, what's the x value of the minimum? So what do? We take the derivative, which is what? Wendy, what's the derivative? 8x minus 4. You take the derivative, and then you set it equal to 0. And this is the technique I'm going to use for the rest of the semester. I will take a derivative and set it equal to 0 and draw a box around it, and that's my new problem. So I took the derivative, that's my function, but I'm going to set it equal to 0, and now I'm going to start working vertically downward here, finding the solution for x. So now I have 8x equals 4, and so x equals 4/8, which really means x equals 1/2. Now what does that mean? The location of the minimum is 1/2 what? It's on the x-axis, right 1/2, or on the y-axis, the minimum is up 1/2. What is the 1/2 referring to? It's not the slope. Well, we know the slope. What's the slope? The slope is 0 because we just made it equal to 0. So we know that it's 0. But our minimum point, the x location is at 1/2. So if I now draw a graph going from here 0 to here 1, then the location of the minimum is at 1/2. So somewhere on this vertical stripe is the bottom of my parabola. The thing is, I don't know where yet. So the parabola could be here, bloop. It could be here, bloop. It could be here, bloop. It could be here, bloop. Which of those parabolas is my parabola? Now how do I find that out? Because all I know for sure is that the slope is flat at x equals 1/2. Where's the vertical location of my parabola? Yeah, you have to plug it back into the original function, right? The original function tells us the y-coordinate. So you see, we actually have to use both functions to locate a parabola. We have to use the derivative to find the flat spot, which is where the bottom or the top is. But then you have to go back to the original function and actually plug in the 1/2 to find out what the y-coordinate of that parabola is. So everybody, in your own calculator, go ahead and plug in 4 times 1/2 squared minus 4 times 1/2 plus 2, and let's see what we get. Whoa. So 4.5 squared. 4. It was at 1. So on my little graph here of all my possible parabolas, I really just had to go from 0 to 1. Then I was going up to 1, and that was the location of the bottom of my parabola. Okay? And we actually don't know what the rest of the parabola looks like. We don't know how quickly it goes up or how quickly it moves to the side. But what I really know is I've got this. I've got that right there. I've got the bitty bottom of my parabola. And so how did we find that? We took the first derivative, set it equal to 0, because that's a flat spot. We solved for where the flat spot was, which was x equals 1/2. And then we plugged x equal 1/2 back into the original function to find the y-coordinate, which nailed down where our parabola was. Now we would have to do more analysis at this point. The parabola could be really tall and skinny. The parabola could be really wide. The parabola could be even wider. Do we know that yet? We don't know that. We have no idea what the parabola looks like. But at the very least, we know where the location of the bottom of the parabola is. So that's the first problem I wanted to do with you. Again, all that's just on a sheet of line paper. What would be the steps? What would you say are the steps of this process? If you want to find a minimum or a maximum, what do you do? Sorry, let me say that again.
Find the derivative.
Yeah, step 1 would be find f prime of x and set equal to 0. Now, just because you set the derivative equal to 0, do you know which one of these things you're about to find? You don't. You have no idea which one of these things it could be. It could be any of these. You know, if you're just looking at some random function and you take the derivative and set it equal to 0, all you're really saying is, hey, find a flat spot. Find a flat spot. You don't know what it is yet. Okay, then what do? You find your flat spot. So, sorry, I should say you solve for x in f prime of x equal to 0. And then you plug, exactly, you plug that x into f of x to find the y-coordinate. And technically at that point, if you don't know anything about your function, like this one, we knew it was a parabola. We knew it was an upward-facing parabola because we knew what parabolas look like. So we knew that we were looking at this. We knew we were looking at a minimum. But technically, if you don't know anything about the function and you just took some function and took the derivative and set it equal to 0, and then found that x-coordinate and then found that y-coordinate, all you really know is that floating there in space somewhere, you've got a little flat spot. That's all you really found at that point, unless you did some further analysis or had some extra knowledge about what your function was. So what is this process for? These are the steps for finding flat spots. That sounds not very sophisticated. What did you learn in calculus today? How to find flat spots. Yeah, kind of silly. So what we really need to know then is something more. We need something more to narrow down what are we looking at. Are we looking at a maximum? Are we looking at a minimum? Are we looking at a transition point? Are we looking at a flat function? What we need is something to know about that flat spot. Is that, like, everybody imagine my pen here is my little flat spot. And if I was like a strong man and this was a piece of metal, I could curve it upward, or I could curve it downward, or I could curve one way down and one way up. Like what we're really wondering at this point is how is that flat spot bent, right? Is it bent upward? Is it bent downward? Is it bent a little down and a little up? Or is it flat? That's what we'd really like to know, right? Because finding a flat spot is one thing, but knowing what that flat spot is another thing. And that's what the second derivative tells us. The second derivative tells us once you've identified a flat spot, it will tell you if it's curved up, if it's curved down, if it's curved a little up and a little down, or if it's flat. And that's what we're looking at for the rest of chapter 2. The second derivative to identify what those flat spots are. But before we do that, let's do another one. This is just another practice problem. So everyone write this down with me on your sheet of line paper, which you have sophisticatedly labeled finding flat spots. So here's the graph of 2x equals 12x squared minus 128, 6x plus 17. It has two horizontal tangents. What does that mean?
It has 2 zeros.
It what?
It has 2 zeros.
Yeah, it has two spots where it goes flat. Two horizontal tangents. A horizontal tangent is just what this is. That's a horizontal tangent. That's a horizontal tangent. This is 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 a horizontal tangent. That's a horizontal tangent. That's a horizontal tangent. A horizontal tangent is just any flat spot. Okay, so let's do our steps. First, f prime of x. So actually, what's the derivative? Yeah. Yeah, perfect. So that's our derivative. And now we just have to solve that for x. So you have a lot of options. You could do the quadratic formula if you wanted to. You could factor it if you wanted to. I think I'm going to factor it. So 6 outside of x squared plus 4x minus 21. Oh, and by the way, I'm so sorry. I didn't even follow my own steps. You set it equal to 0. Right? Whatever your derivative is, you set that equal to 0, and now you're starting a new problem. So now I'm going to solve this for 0. I'm factoring out the 6. I divide off the 6. Now I just have x squared plus 4x minus 21. And how does that factor? What two numbers multiplied to make 21 that had to make 4? Yeah, 7 and 3. So x plus 7, x minus 3. And using the zero product rule, either x plus 7 is equal to 0, or x minus 3 is equal to 0. And so x equals negative 7, or x equals 3. Now we're going to do this problem all the way through. So let's just imagine, what do we really know right now? Because we don't really know what this looks like. I mean, I don't think a lot of us walk around thinking, oh yeah, that type of problem with a 2x cubed, that looks like this. You know, we don't know, unless you have a graphing calculator. So let's look at our steps. We found f prime, we set it equal to 0, we solved for 0, and what did we just find? What are these things called?
0.
They're critical points. Another word for critical point is flat spots, right? Critical points, flat spots. So all we just did right now, let's start drawing a graph. We have a graph, and I'm saying that over here at negative 7, 1, 2, 3, 4, 5, 6, 7. At negative 7, I have a flat spot somewhere. And at 1, 2, 3, I have a flat spot somewhere. Do I have any idea where the flat spot is on this vertical stripe? I have no idea. The flat spot could be anywhere along there, but I have no idea. What about my flat spot at 3? It could be anywhere. It could be down here, it could be here, it could be here, it could be here, it could be here. I have no idea. All I know is that somewhere along these two stripes, I have a flat spot and a flat spot. If my flat spot was here and my flat spot was here, I could go ahead and guess that my function looked like that. Right? That would just be a guess. Or if, I just ruined my graph. If my flat spot was here and my flat spot was here, then I could guess my function looked like this. That's really it, right? Could it be that my flat spots were both here and here? Could that be the case?
Mm-hmm.
Really? Because there were only 2 flat spots. Yeah, there were only 2 flat spots. If I put them at the same level, then if I went like this and then stayed like that, I would have found a lot more flat spots. So it couldn't be like that. And if I had gone from here and then came down and then back up to there, then what? I would have had another flat spot. So that tells me that those two flat spots have to be at different levels from each other. So it has to be that, say, one is up high and one is down low. I just don't know where. So how do we find out the y-coordinate? Plug it back in. So everybody go ahead and plug into your calculator. Find the y-coordinate of those flat spots by plugging. Do we plug -7 into the slope or into the formula? The original function. What would I get if I plug -7 into the equal? It would equal 0. That'd be obvious. Like -7 is the flat spot. So the slope would be 0. So there's no need to plug -7 equals -7 into the, so 2, -7 cubed plus 12, -7 squared, minus 126, -7, plus 17. My calculator was off. Isn't that just the worst? So 6, -7, no, 2, -7 cubed plus 14 squared minus 126, 7, and plus 17. Did anyone else get 801?
Yes.
801? Is that what you all got? So at -7 is, I don't have to draw a graph to scale. All you got to do is just put a tick mark that says 801. And so there was our first flat spot. Wait, really, did everyone get 801? You plugged it in? Okay, so now you hit second enter. You go back, you just change all those -7s conveniently into degrees. If you're not sure how to hit second enter and just edit the equation, make sure you see me so I can show you how to do that. The second one is at -199. Did everyone get that? -199. So there's my other flat spot. So I now know that I have a flat spot at the coordinate 3, -199. I have a flat spot at the coordinate -7, 801. And so what does our graph look like?
Like number 4, my transition.
It won't be a transition point. These are both going to be genuine maximums and minimums. That.
Okay.
Yeah, that's what it would look like. And look at the power of what we just did. We have a pretty good graph of this function, and we didn't even use it. That's incredible. See, this is what allowed Newton and Leibniz and other mathematicians in the 1600s to actually know what they were doing. Because that was 400 years before calculators and computers. They didn't have graphical readouts, or all they had was their Newton depths calculator. Literally, this was their graphing calculator. All right. Well, folks, that is how you find maxima and minima. Specifically, that's how you find critical points. And the critical points could be maxima, minima, transitions, flat, or I don't know what those things are. So that's our essential question. How do you find the min-max of a curve? And what we really just found was, how do you find the critical points? That is, the flat spots. What we're going to start talking about today is to know, is that flat spot being bent downward? Is that flat spot being bent upward? Is that flat spot being bent in 2 different directions? Or is it just genuinely flat? And that's what the second derivative is going to tell us. So here we are. Today's March 1st. We're doing section 2.6. We have spring break coming up in 2 weeks. So sad. Do you guys want to meet anyway?
Sure.
We can just come on down campus. They'll open up the doors for us. We'll have class anyway. We can meet where?
Yeah.
Sure, we'll have class in Rocky Point. All right. Well, oh gosh, I didn't give you guys new jokes. I don't know what those jokes are. I think I didn't tell you a joke though. What's today, Thursday? Did I tell you the one about the scarecrow?
Yeah.
Okay, so I didn't tell you the one about the bear without teeth. What do you call a bear without teeth? What do you call a bear without teeth? All right. So folks, chapter 2a and 2b. there's this distinction in chapter 2 between the first half of chapter 2 and the second half of chapter 2. The first half of chapter 2 is what we already did. In the first half of chapter 2, we learned about slopes, secant lines and tangent lines. We learned about taking limits, about continuity. We learned about the difference quotient, how to take the derivative and formulas for derivatives, and then some applications to business. That's what we did in chapter, in the first few sections. In chapter 2b, so sections 6 through 10, we will learn about taking the second derivative, the derivative of the derivative, and what that means and how to find and apply the first and second derivative to solve problems. So that's what we're starting today, is the second derivative. So, essential question, what do each of these things tell us? So everyone should be able to tell me what the first thing tells us. What does the function tell us? The y-coordinate. And what does the second thing tell us? Slope. What does the second derivative tell us? Oh, good. The slope of the slope. That's correct. It tells us the slope of the slope, right? It's the slope of how the slope is changing. That doesn't make a lot of sense, though. Like, it's kind of hard to think. So let's prime a telling of how the slope is changing. Okay, so what we're really doing is finding the rate of change. That's even better. I'm going to take back that. It's the rate of change of the slope. So let's try that. Let's pretend I'm going to start a function right here, and I'm going to start it off with a positive increasing slope. Okay? But now over time, what I'd like to do is start decreasing the slope. So over time, I'm going to take the slope I started with, and I want to start decreasing the slope over time. What does that mean to decrease the slope? It would go from here to here to here to here to here to here to here. I'm decreasing the slope over time. So let's just start making a bunch of slope indicators. My next one, I'm going to make it a little less steep. And my next one, 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 a little less steep. And then less steep, and then less steep, and then less steep. Looking at that picture, would you agree that the slope is changing over time? Yeah. And specifically, is the slope increasing over time or decreasing over time? It's decreasing over time. We could put numbers on these things. This would be like plus 1 over 1, and then this would be like plus 1 over 2, and then plus 1 over 3, and then maybe plus 1 over 4, and then maybe plus 1 over 5, and then, oh, I didn't give myself a 0 point, a 0 slope. And then it'd be going down 1, right, 5 maybe, and then down 1, right, 4. So these numbers are definitely decreasing. You could look at them on a number line and see that you're going from, 1, and then you're moving left on the number line to the negative number. So the slope this over time. What about a slope that increases over time? Like, let's just say that I started with a negative slope, and I'd like to start increasing the slope over time. So, facing you guys. No, yeah, this is you guys. Facing you guys, that's negative slope, right? Okay, so I want to start increasing my slope over time. So I'd go from here, increase it a little bit, 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 increase the slope, increase the slope, increase. So let's try that. If I'm starting with a negative slope, but over time I want to increase the slope. So first I increase it a little bit, I increase it a little more, 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 and I increase it a little more. That's what it would look like if I increased the slope over time. Right? So I'm starting with a negative slope, and then still negative, and then still negative, but then it hits 0, and then it starts increasing over time. The second derivative tells us the rate of slope. How quickly does the slope change? That's what the second derivative tells us. There's a much faster to say what the second derivative tells us. Okay, and it's a one-word answer. So f of x tells us the y-coordinate. F prime of x tells us slope. F double prime, F second derivative, tells us concavity. Have you ever heard of the word concavity? Because that's what this is. The word is concavity. I think we've all used the word concave, at least at some point in our life. What is something that is concave? What does that even mean? Or maybe what are some objects that you have at your house that are concave? Or maybe some objects that you have on you that are concave. Do we ever use the word concave, Daniel?
Like a cup, right?
Yeah, cup is concave. I mean, maybe I'll start with a soup ladle. Like, let's say that this is a soup ladle. Is that not the best soup ladle you've ever seen in your life? So the ladle itself is concave. Speaking of spoons, a spoon is concave. Right? So there's a spoon. It's a silver one. So there's a spoon. A spoon is concave. Okay? What else might be concave? The entrance to a cave. Here's a cave. Literally, cave, concave. It means that you could go into the cave. Because, you know, you walk up to a mountain, there's a mountain, but then there's an indentation into the mountain, and that is a cave, literally. So what does concave mean? It means it's indented. All right, it's indented somehow. And concavity can either be concave up or concave down. That's concavity. You really only have two options. So concave up is a positive because the concavity is pointing up. You could hold liquid. And concave down is negative. So no liquid would be held at all. That'd be more like an umbrella. If concave up looks like this and concave down looks like this, what would concave 0 mean? If your concavity were 0, what would you look like? Just perfectly flat. There's no concavity at all. So concave 0 means flat. So again, going to my strongman reference, or like a circus, a strongman or a strongwoman, they take a metal bar and then they bend it, or they take the metal bar and they bend it. Have you ever seen anybody bend a metal bar? Can you imagine it from a TV show maybe? Anyway, that's essentially what we're talking about. So concave up means that that flat piece of metal has been bent up. Concave down means it's been bent down. And concave 0 means that it's still flat. So this concept of concavity is going to help us figure out which critical point it is. Is it a minimum? Then it's concave up. Is it a maximum? Then it's concave down. Is it neither a minimum nor a maximum? It's perfectly flat. So we use this idea of concavity to tell us about those critical points, whether they're minimums or maximums. Okay, well, folks, that's our word, concavity. So f of x is the y-coordinate, f prime of x is the slope, f double prime is the concavity of a function. And I think that's what I have right here. You know, the y-coordinate, the slope, the concavity. Or as Luis said, the slope of the slope. All right. So what does the second derivative tell us? What does this second derivative tell us? Well, first of all, it tells us the concavity of the original graph. So it tells us if the original graph was concave down or if it was concave up. It also does tell us technically the slope of the derivative graph. This is all worth writing down. Right? What is the meaning of the second derivative? The meaning of the second derivative is that first and foremost, that's the concavity of f of x. Right? It's the concavity of the original function. Whereas it could also be considered the slope of f prime of x. You know, you take the derivative and then you look at that graph. Well, that graph has slopes too. And so you're technically finding the slopes of the derivative. And then in a total other context that we're going to talk about soon, just ignore number 3 for now. We'll get to that. Although I guess, well, no. Okay, we already talked about it once. We can go ahead and talk about it. We talked about a distance versus time graph. So we had distance versus time. And we said that if you look at a particular graph of distance versus time, that every slope that you look at was velocity. It's been a while since we've talked about that. But do you remember us talking about that? That if you look at a distance versus time graph, distance on the y-axis and time on the x-axis, then if you take the slope at any given point, that's actually telling you the speed of the vehicle. And so if f of x represents distance from home, and f prime of x tells you your velocity at the moment, f double prime of x actually represents your acceleration in your vehicle. That's interesting. Folks, how do you know if you're accelerating or not?
The angle positive reason.
Oh, well, that's true. I mean, you could look at a graph and figure out if you're accelerating or decelerating, but I mean in a vehicle. What do you actually feel if you're accelerating? Like, let's say you're in a car with someone else and they step on the gas. What do you feel? You feel pressure, right? You feel yourself like either pushed back into your seat, or if they slam on the brake and you decelerate, you feel yourself lurching forward. So acceleration is something that you literally feel, right? You can feel yourself accelerating. Whereas, can you feel velocity? Like if you're just sitting in your car and you've got cruise control and you're on nice flat level ground, and if you shut your eyes, don't do that if you're driving. But if someone else was driving, would you even know that the car's moving? You technically wouldn't even know that the car was moving. So velocity is something you can't feel, but acceleration you feel. Right? Okay, so that's what the second derivative will represent. And we'll do some problems like that, where we talk about distance, velocity, and acceleration.
Would be similar to like Earth moving.
Yeah, exactly. Like the Earth is moving right now, but we don't know that. Yeah.
We know it, but we don't feel it.
Yeah, we know it, but we don't feel it. Well, I don't know. I don't know if we know it. The Earth could be flat and it might not be moving. No, I'm kidding. It's probably not flat. It probably is moving. That would be my guess. All right. So these are notes from your textbook. So if you had already read chapter 2.6 before you came in, you would have seen these pictures. They just have some nice pictures here of what concave up looks like and what concave down looks like. And then they have got this really nice graph down here at the bottom showing you how a function can change from concave up to concave down, to concave up to concave down. And what do you notice about every portion of a graph that's concave up or down? So like, what does this portion have?
Oh.
It's got a minimum. And what does this portion have? A maximum. And this portion, a minimum. So typically, every portion of a graph that you look at, if it's concave up, there's probably a minimum there. And then if it's concave down, there's probably a maximum there. I'm not going to do that example. Okay, well this is just telling us how to write that. So how do we write the second derivative? The most common way is to write f double prime of x. If we're dealing with y, it would be y double prime. And if we're dealing with d dx, you would either write d squared y over d squared x, or you could write d squared f over d squared x. Those are all notations that represent the second derivative, which is telling you the concavity.
So if we see any of them, we should know that each, like.
All of those mean second derivative. And you can either say second derivative, or you can say y double prime, f double prime. Okay. Now, we just barely heard the word concavity, or no, critical point. So when you set the first derivative, gosh, where do I put these in your notes? I mean, you're all taking notes, and I'm just giving you more and more information. But remember when you, I'm going to get rid of all this now. As far as notes go, when f prime of x, when you set f prime of x equal to 0, you find critical points. That is flat spots. Okay? So that's if you set the first derivative equal to 0, you just found what we call critical points, and those are just all the flat spots. Where, again, those flat spots could look like lots of different things. It could be the bottom, it could be the top, it could be a transition point, and it could be just be flat. That's what you find when you set f prime of x equal to 0. You find all those critical points which are just flat. On the other hand, when you set f double prime of x equal to 0, you find what are called inflection points. And an inflection point is when concavity changes. When concavity changes from concave up to concave down. There we go, concavity, an inflection point. So an inflection point is when the concavity changes from concave down to concave up. So that would be an inflection point. Because to the left-hand side, it was concave down, but to the right-hand side is concave up. And so that special point right there, it may or may not be flat, but it's definitely an inflection point because the concavity is changing. Just to make it more clear that it doesn't have to be flat. It could be like that. That's still an inflection point because you're changing from concave up to concave down. So anytime you set the second derivative equal to 0 and solve for x, you're finding an inflection point, which is where concavity changes. I know I'm giving you a lot of information. I'm giving you a lot of new terminology and vocabulary. So let's take a look at these points and try it. I want to know, out of each of these points, is the concavity changing right there? Is it changing from concave up to concave down? Or from concave down to concave up? So how about point A? Do you have a different type of concavity to the left and right of A? What is it to the left of A? Concave up. What is it to the right of A? Still concave up. So point A is not an inflection point. It's a critical point because it's flat at the bottom, but it's not an inflection point because it's concave up all the way around it. Okay, how about point B, folks? What type of concavity is to the left of B? Concave up. What kind of concavity is to the right of B?
Down.
Concave down. So B is an inflection point. B is an inflection point, but it's not a critical point. It's not flat, but it is where the concavity is changing. How about point C? Is that an inflection point? What kind of concavity is to the left?
Down.
Down. What type of concavity is to the right?
Down.
Down. So no, C is not an inflection point. It is a critical point because it's flat at the top. Okay, how about point D? What type of concavity is to the left? Down. What type of concavity is to the right?
Down.
Still down. So D is not an inflection point and it's not a critical point. What about point E?
Yes.
What type of concavity is to the left? Concave down. This whole thing here is concave down because it's like a bowl that's turned upside down. So to the left of E is concave down. What about to the right of E?
Down.
Also concave down. So E, well, it certainly didn't change from concave up to concave down. An inflection point is the point on the graph where the function, where the concavity of the function changes from up to down or from down to up. So no, E is not a concave, it's not an inflection point. Okay, so F, is that an inflection point? No, because it's down all the way around. What about G? Is that an inflection point? Yeah, because it goes from concave down over here to concave up over here. Okay, well anyway, folks, that's an inflection point. Yeah, working definition of inflection point is a point on the graph where the second derivative changes sign from plus to minus or from minus to plus. Okay, so that's an inflection point. Oops. And, okay, well that's it for now. Let's try some problems. Let's try some problems, folks. I gave you all your packet for 2.6. Let's see how all of this works out in practice. And from here on out, folks, we're going to probably use f of x, f prime of x, and f double prime of x simultaneously. We'll use all three of them in any given problem to give us an understanding of what the graph looks like. Now, admittedly, a lot of what we're going to do could be answered by just looking at a graph. Okay? For almost any one of these problems, we could answer it by just going to Desmos and graphing it. But what we have to do is pretend that we're Newton and Leibniz in the 1600s and we don't have a graphing calculator available to us. And so we're doing these things by hand to learn how to do it. So let's start the first problem, but before we do, let's look at it. What does 7x to the 5th minus 3e to the x look like? Before I show it to you, do you know what 7x to the 5th minus 3e to the x looks like? Of course we don't. We have no idea, right? That's what we'll be doing for the rest of this class is looking at functions and we have no idea what it looks like. Look at the next function. Do you know what 6 plus 5 over x plus 3 over x squared looks like? We have no idea. And so what we're trying to do for the whole rest of the class is to find out what these functions look like without using a graphing calculator. That's the tools we're learning. But the irony is, I'm always going to show us a picture of the graph. Right? So I'm going to show us a picture of the graph while simultaneously telling you our job is to figure out what the graph looks like without looking at a graph. So what does this graph look like? Whoa. What happens up there? Does that ever end? Is there a top or does it just go up forever? I can't see the top. Well, my goodness, it looks like it goes up forever, but that doesn't make any sense. What did our graph?
It comes back down.
Yeah, this is a crazy graph. And yet, wasn't there a wiggle somewhere? Oh, there was a wiggle. Bloop, there was a wiggle. So this is strange. What does this graph look like? It appears to be a gigantic upside down parabola with a wiggle. And look how tiny that wiggle is. I mean, you could have easily missed it, right? I mean, if you're zoomed out far enough, would you have ever noticed that wiggle?
No.
Never, ever. And yet, what special property does that wiggle have? It's got two of them. It's got flat spots, it's got critical points, and also, what else does it have? Besides two critical points, it has an inflection point too. So actually, this little wiggle, that if you were zoomed out and you wouldn't have even noticed it, this little wiggle is, calculus-wise, very interesting because it has two critical points and an inflection point, and we can solve those using our formulas. What does the rest of the graph look like? It is just one great big upside-down looking parabola. The top is way up there somewhere, I don't know where. Really far up there. Okay, so now let's start analyzing. Now that we know what we know. It says, first, find the derivative. So everyone, let's do number one. You all have did everyone have one? Okay. So, number one, f of x is 7x to the 5th minus 3x to the 3e to the x. Okay, and the first thing they want us to do is find the derivative. All right, what's the derivative of the first part, Rosa?
35x to the 4th.
Yeah, 35x to the 4th. Now we have to review, what's the derivative of e to the x? E to the x. It's the one function whose derivative is itself. And what does the 3 do? It just comes along for the ride. So that's just minus 3e to the x. So that's f prime of x. And what are they asking us to do? Find f prime of 3. Well, that seems a little arbitrary to me. So we're finding f prime of 3. Let's cheat. F prime at 3, well, 3 is way up there. I don't even know where 3 is. But it's really far up there. What do you think is happening at f of 3? It's either on its way up or it's on its way down, right? Because the graph is between 0 and maybe 15. It goes all the way up there and then comes back down. So I don't even know where 3 is. Did we find it? X equals 3. It's somewhere up there. Hey, now we can all take a guess. At x equals 3, is it on its way up or on its way down? Looks like it's on its way up. So what should our answer be? The slope is going to be positive. So let's find 35, 3 to the 4th, minus 3, e to the 4th. So that's 35. What's that?
When the power form is like 3.
Oh yeah, sorry, that's 3. Thank you. So 35 to the fourth minus 3 e to the 3. And did you all get 2,774? Okay, so what does that tell us? It tells us on our graph that it's just really, really steeply positive. Like it's shooting up there. It's still increasing at an alarmingly fast rate. What else did it want us to find? The second derivative and the second derivative at 3. So let's find the second derivative. Who'd like to do that for us? Take the second derivative. Kristen, what's the second derivative?
When are we just?
Yeah, 4 times 35. You can take it one step at a time. What's 35 times 2? 70, and then 70 times 2 again? 140. So 140 x to the third. But yeah, by all means, Kristen, always have your calculator out. It's so much easier just to do these things on a calculator. Then you don't make a mistake like I do. And then what's the derivative of 3 e to the x? Same thing, just 3 e to the x. Okay, so now that's our second derivative, and we want to find out the second derivative at 3. So notice, we already know that at f of 3, it's steeply increasing. And now we're about to find out, is it steeply increasing concave up, or is it steeply increasing concave down? So what happens when we plug in the 3? (140) 3 cubed minus 3 e to 3. What did you all get?
37.
Yeah, 3,719.7. So what is it, concave up or concave down? It's concave up. So this problem didn't exactly ask us to do much. But if we just go ahead, now, here's our key thing here. We want to draw a picture of that point on the graph. So do we even know where it is yet? What's the y-coordinate? We didn't find out, did we? Let's find out the y-coordinate real quick. What's the y-coordinate? F of 3 is what? So if I plug that in, that's 7, 3 to the 5th minus 3 e to the 3rd. What was the y-coordinate? Did anyone else get 1640.7? Anybody? I'm just waiting for confirmation. Yeah. You're just saying that. What's the actual y-coordinate at this point? Is that what you got in it? Okay, all right. So folks, here's what I want us to draw now. Let's draw a picture of what that point looks like. So at f of 3, there's a coordinate way up here whose y-coordinate is 1640. And furthermore, what's the slope right there? Steeply positive. So we'd make a really steeply positive slope indicator. And furthermore, what's its concavity? Positive, right? So it's concave up. So I would very slightly go like that. That's what we just found out. We just found out, like if all we had was a little peek hole on the graph, and we just zoomed in, and all we did was look right there, we would at least know that on that weird graph, that point is increasing, it's concave up, and it's way up here at 1640. That's what all three of those pieces of information told us together. The y-coordinate told us it's way up here at 1640. The first derivative told us that it's increasing, and the second derivative told us that it's concave up. Yep, that's what we just found out using calculus. If you didn't have a calculator, a graphing calculator to actually zoom in right there, we just found it all analytically using these three tools: y-coordinate, slope, concavity. And together, those allow you to zoom in and know what a graph is doing at one spot, even if you don't know what the rest of the graph looks like. So we'll take a break, but then we're going to do the exact same thing with this function. We're going to zoom in on the point 2 and be able to know where is that coordinate, what's its slope, and what's its concavity. So let's take a break. It's 1202, let's come back at 1212.
What was that?
it's split up into two sections. You get some. Okay, I'll just take the red one too. I know that's sort of like either 9 or 12.
What version is it? What version is it? What did you guys do? This time back. No.
Oh, didn't you show up like after that? Didn't you show up like after that?
No, not yesterday.
I thought you were there. Now you know what you're wearing. And neither was the guy that sits next to you. Neither was the guy that sits next to you.
Oh.
We just talked about chapter 19 and learned a lot of new things actually. Do you know anything about the test though?
No.
What did you get?
Were you back for?
Yeah.
I don't remember. I left it at home.
And I got a new one look at it.
Like, I understand everything, like, when we're doing in class and, like, at home. I don't even look at my notes when I do my homework. When it comes to test and translation. I'm just lost.
But some people did good. They got like 40. Well, I guess that's good enough for them. Anyway, I wouldn't do that.
I think she makes it really long because, like, each word, like, you know, like, each pause, I think about, like, 4 or 5 minutes.
Oh.
You know what I mean? Like, the whole thing reading and stuff.
I always put everything else alike. That's why sometimes I put the wrong thing.
Mm-hmm. And the other thing, like, a lot of problems look similar.
Mm-hmm.
And then, like, you just end up getting it wrong anyway.
She didn't say anything about extra credit.
I
I'm
know.
really bummed about that. I had a meeting, but if I can't, this is what I need to Oh, I think I said 0.10% away from an A last semester, and she didn't round it up.
Mm-hmm.
I was like,
No, like, I was next to me in ticket. Like, he's really picky about his grade, but, like, he says that class is, like, a little bit harder for him. He was only point away from being a B2, and then she didn't turn off, you know.
like not even 1 point, it's like 0.10. Like 1/10 for a point. And she didn't round it up.
Mm-hmm. Yeah, I mean, I gotta stay in her class too, and all the way from B. And she ran it. And then she gave me the work at the end of the semester because I was like, I was not doing so good. Because I had missed few assignments. Remember the last one she gave? Like, it was like a long one. It was like a 4.
Oh, that was an assignment. That was like part of the, not the final, but
Yeah.
something.
Yeah, so I didn't do that one. You know, that one was like a lot.
That's like,
Yeah.
oh, great.
Yeah, so then I didn't, like, I did half of it. So she told me she was gonna open it up and she wanted me to do it before the final, which I did. It took me like 2 days in a row to finish it. But I finished it and I got a good grade. I got like a 94, 95 on it now. So my grade went up like dramatically.
Yeah. I wanted to see the note on it, like the feedback. Yeah, no, the whatever that thing was called, happening, the big package.
Oh, the last assignment that we had on it.
But I wanted to see like how I did on it because I actually had a lot of fun going. But I never found it. She never gave us the paper.
This class is a little bit easier. Like it's easier because everything is just like what is. But those what is are like make you think like 2 times. You know what I mean? Like the top, like the top. Right now, like the 13.
Oh.
So you know how she's like, what we all call like what is. You know how she really like two options, like not 2 options, but two ways to think about it. And then one is right and the other is wrong. And then like you're just like that way you get a little bit confused.
All right, folks, let's try that again. So again, as we move forward, we're going to use all three functions, the regular function, the first derivative, the second derivative, in order to say as much as we can about one point in space. So I believe number 2 is fairly similar to number 1, so let's go ahead and try it. And you'll notice that at no point did they ask us to find the original function evaluated at 2, but let's just go ahead and do that. We always want to plug the value into all 3 functions. So here's f of x. And folks, even though it's 6 plus 5 over x plus 3 over x squared, what do we have to immediately do to this so that we can take the derivative? We have to move those variables up into the numerator so that we can do the power rule. Okay, well first I'm going to go ahead and calculate it. So f of 2, how do I know that we're doing 2? Yeah, that's the number they're telling us to plug in later. So let's find f of 2 in our calculator. That'd be 6 plus 5 over 2 plus 3 over 2 to the square. Did anyone else get 9.25? All right. So there's the function. Now we'll go ahead and take the first derivative, which I have to rewrite this. So that's 6 plus 5x to the negative 1 plus 3x to the negative 2. Did anyone else get that? Just to rewrite it. Okay, so the derivative. What did you get for the derivative, James? What's the, go term by term. The derivative of 6 is 0. The derivative of 5x to the negative 1
is going to be 5 to the negative 5.
Yeah, negative 5.
And the negative second.
Yep, that's correct. You bring down the negative 1 and multiply it by the 5, so that's negative 5, and then subtract 1 from negative 1, which is negative 2. And then what's the derivative of the next one?
-6.
Yep, negative 6.
And negative.
Yeah, perfect. So you bring down the negative 2, negative 2 times 3 is negative 6, and then negative 2 minus 1 is negative 3. So folks, that's the first derivative. And honestly, the only reason to convert it back is just to make sure you're typing it into your calculator properly. You know, it probably looks a little better if we say f prime of x is negative 5 over x squared minus 6 over x cubed. And now we can go ahead and plug in 2. I mean, you could just plug 2 into this, but you have to be very careful with negative exponents that you put that negative exponent in a parenthesis when you type it into your calculator. So whichever way you want to do it, everyone go ahead and plug 2 in, and let's all check to see if we get the same number. So.
Just one question.
Yeah.
Where did you get the x square from? Wasn't it just regular x?
We're here. This is the original function that I wrote with negative exponents. And then we took the derivative to get to there.
So I was just wondering because when you wrote it down on the bottom, it says x squared and on the actual.
Oh, right, because now I pushed this x to the negative 2 back down into the denominator. Okay, good question. And then minus 6 divided by 8. Did anyone else get the answer is negative 2? So however you type that into your calculator, whether you typed it in as negative 5 times 2 to the negative 2 minus 6 times negative 2 to the negative 3. Or if you typed it in as negative 5 divided by 2 squared minus 6 divided by 2 squared 2 cubed, you better get the answer of negative 2. And if you didn't, then you want to go back and figure out how to use your calculator to calculate.
I was just wondering for, how you drop down to,
Yeah.
do you want it written like that or is it?
Well, so here's the thing. I mean, this would be the final answer for f prime of x. If you were just done there and you wanted to know what f prime of x was, you would write it like this. But the fact is, we're now going to do the derivative of the derivative, and we need it written like that to do the second derivative. So this way is more useful. This way is the final answer. Did that answer your question, Kristen?
Yeah.
Okay. All right, so now, folks, let's find the second derivative. The second derivative. Now we take the derivative of the derivative. And so we need it still written with the negative exponents. Daniel, what's this derivative?
Negative 10x.
I think at negative 10.
10,
Yeah, 10.
10x to the negative 1.
Yep. And then?
Plus 18x to the negative 4.
Yep, very good. So now that's our second derivative. What's that, James? Oh, that worked, okay. Which I will go ahead and write that in final form. That's 10 over x cubed plus 18 over x to the 4th. And now we'll go ahead and plug 2 into that. So f double prime of 2. And then I type that in my calculator. 10 divided by 8 plus 18 divided by 18. Did anyone else get 2.375? Okay. Now, here's the fun part. We now take all this information, the fact that the y coordinate is 9.25, the slope is negative 2, and the concavity is 2.375. We take all that information and we draw a picture of that point, just that point. Like, as though we're just looking through a little tiny peephole to look at that part of the graph, and that's it. So, what will our graph look like? We're going to the x value of 2, and the function has the y value at 9.25. And now I know that's where my coordinate is. Right, so that's just taking the information of the function itself. The x value is 2, the y coordinate is 9.25. So there's my point. Now what kind of a slope should I get? Negative 2, so it'll be a negative slope. And I'll go ahead and give it a little slope indicator that's negative. So I've got my negative slope indicator. Now, folks, this graph that I'm drawing, please draw the graph. This is the most important thing we're doing. All of that was just scratch work, right? That's all just scratch work. That's just us doing the calculations. This is the actual product. So now you give the negative slope indicator now. Is it concave up or concave down? Yes, it's a positive concavity, so it's concave up. So you just give it a little slight indication of the fact that it's concave up. And that's it. That's the end of that problem. It's like, woo! You know, we did all that work. And yeah, just that teeny little bit right there of what's happening right there. Now, what's happening in the rest of the graph? We have no idea. Maybe the rest of the graph goes, wee, zoop. And it goes over here, wee! I mean, nobody knows. We don't know. I don't know. But we know for sure that that's what the graph looks like right there. The power of calculus. Right? Now, of course, what can we do right now? We could graph it and find out if we did it right. So I'm going to go ahead and graph that particular function, which is 6 plus 5 over x plus 3 over x squared. All right. And I got to get back to the origin. Gosh, home. There we go. I'll turn off that. Hey, okay, so here's the function. Now, first of all, did anybody guess that the function would look like that? Yeah, that's a wild and crazy graph, right? Okay, but now where were we looking? X equals 2? I'm going to go ahead and draw in the vertical line. Well, actually, I can just find x equals 2. There's x equals 2. How did we do? Good. Is that what we said it looked like?
Yeah.
We nailed it, people. Look at that. We nailed it. It's at the coordinate 2, 9.25. It's negatively sloping, and it's concave up. The power of calculus. Now, folks, I don't know if you're impressed or not. I have no idea. You might be underwhelmed, you might be overwhelmed, you might be whelmed. But in the 1600s, when Newton and Leibniz were doing this, this was like top of the line. This was like, man, you can draw that little part of the graph, you're cool. Right? That was advanced technology at the time. All right, let's keep going. Number 3, totally different type of problem. This is just looking at our conceptual understanding of function, derivative, concavity. So what are they saying here? The function graphed above is decreasing on that interval, and the inflection points are where? So when is the function decreasing? From when to when?
-3 to.
Yeah, -3 to -0.5? Okay, well, that's it. That's all I want to know for that part. Just the function is decreasing from -3 to -0.5. So from -3 to -0.5. However, where is the inflection point? So remember, inflection point, let's keep our vocabulary straight. Critical points are flat points, where it's flat. Where are my critical points? Here and here. These are critical points because those are the flat spots. Where's the inflection point? The inflection point is where the concavity changes from concave down to concave up. So where's the inflection point, do you think?
Goes to 2, but less than -2.
Somewhere in there, right? Like, depending on where I put my finger, I could argue that looks concave up, that looks concave down. So I'm thinking where my finger is pretty good. Now, could that still be it? Yeah, maybe. Could that still be it? Yeah, maybe. It's just somewhere in there. So what should we guess? -2 seems perfectly fine to me. I'm sure Math.AS will accept a range of answers from you. I think if you answered anywhere from -1.5 to 2 and a bit, you would have the right answer.
The inflection point is always going to be the big one.
The inflection point is where the concavity changes from concave down to concave up. So it looks like that point there under my finger is the transition point. Now, how would you actually find the transition? Sorry, how would you actually find the inflection point? You would have to take the second derivative and set it equal to 0. And then you would find the actual inflection point. Well, we don't even know what the function is, do we? They didn't tell us. So we have no idea. Okay, number 4, we're going to save to the end, because I wanted to make sure that we can get through everything else. Number 5. All right, here's a fun problem. Number 5 is, suppose that the position of a particle is given by that. So that's the position. I'm going to draw a graph. I hope you do too. The position, generally speaking, what does that graph look like? Maybe we don't know, because it's a cubic. What does a cubic look like? A cubic looks like this. It comes up, and then it goes up again. That's what a cubic looks like. So honestly, this is one situation where looking at the graph could be pretty helpful. So I will go ahead and get us a picture of this graph. So 5x cubed plus 3x plus 9. So what does our graph look like? Not wildly exciting. It comes up, it transitions, and it keeps going up. So that's what our particle, that's the distance over time graph. Yeah, it's really not exciting at all. Look at it. Super lame. In any case, that's the position of the particle. What do they want us to find out?
The velocity.
Find the velocity. So, folks, if you would, start this problem by writing down some definitions with me. Represents position or distance. F prime of x represents velocity, and F double prime of x represents acceleration. Just generally speaking. And what are they using? They're using S, V, and A. So S, in this case T, S of T, v of t, and a of t. So I think it's obvious why they use the letter A. A stands for acceleration, B stands for velocity, S is the Latin word for displacement starts with the letter S. I forget what it is. But they didn't use the letter D for distance because D was already used by some other equation. I forget now off the top of my head. But S classically in physics means distance. Okay, so that's what we're looking at. And they told us what? In this particular case, our position particle is S equals f of t, which is 5t cubed plus 3t plus 9. And the first thing they want us to do is just find the velocity function. So what do we do? We take the first derivative, which will be our velocity function. So that should really say s of t. So the original function is s of t, which is the position. The first derivative is v of t, which is what? Let's see here. Karina, what's my derivative?
15
15.
squared.
V squared
3.
plus 3. So there's our velocity, and they asked us to go ahead and find the velocity at time 3. So the velocity at time 3, we might even be able to do that off the top of our head. 3 squared is 9. 9 times 15 is something. 135 plus 3, 138. 138 what?
Second.
Did it tell us?
Yeah. Find out that time.
Oh, you're right. Meters per second. Okay, they did tell us. It's meters per second. 138 meters per second. Did I get that right, by the way? 138? All of you checked the math, right, on your calculators? Yeah, right? You're using your calculators all class long? I should glue those calculators to your hand, folks. That's how frequently you want to be using your calculators in here. Okay, so now, did anyone confirm my answer?
Yeah.
Okay, good, thank you. I just did that off my head, folks. I could be wrong. Okay, acceleration, what do we do? We take the derivative again. So now f double prime of t. What's the second derivative, Rosa? I'm sorry, what's the derivative of the derivative?
30.
Yep, 30t. So that's our acceleration function. And we want to find acceleration at 3. So that would be 90 meters per second squared. In keeping with this incredible technology that we have here, can we draw a graph of what we just found out? Yes, we can. It's so fun. I love it. Yeah, we can. So where's our position? We're looking at 3, right? So where was our position? Oh, we never even did calculate the position at 3, did we? Remember, we want to do all 3 every time. We want to find the function at 3, the derivative at 3, the second derivative at 3. So what's the function at 3? We'd have to use our calculator. 5, 23.
153.
Plus 9. Did you get 153? Okay, so at 3, the position is actually at 153. So that's just the position on the graph. What does our first derivative tell us? Is the slope positive or negative? Positive. So now we know that our slope indicator will be positive. And what does the second derivative tell us? Is it concave up or concave down? Concave up. So I would put a slight curve on that. And that's it. We just got a little teeny snapshot into the world of this particle. At 3 seconds, its position is increasing over time, concave up, which means it is accelerating. I think in the future, we should just make a best practice of immediately plugging that value into the function so we already know, we want all 3 values. All right. That's it. Now, folks, what's the final answer? Is the final answer this, and this? Kind of. That's part of the final answer. But this is the final answer. This is a visual representation of what we just learned. This is something that somebody else could really appreciate. Okay, continuing on. Number 6 says let a distance function be given, find the velocity. Ooh, this question is different. Everyone go ahead and read the question. What do they want us to find? Yeah, and
Did we skip number 4?
we skipped number 4. I said we would just come back to it at the end, provided we had time. So what do they want us to know? What about velocity? The first thing they want is a function for velocity, but then what do they want us to find? No, when velocity is equal to 0. And since velocity is really the slope, we're finding the flat spots. The flat spots on our distance. And then they also want us to find acceleration. So let's do everything. Let's really look at everything in this particular problem. Let's map out the whole picture of this graph because it'll be interesting, very interesting. So I'm going to come over here. I have a little more space. So let's go ahead and begin with the original function, s of t, which is 4t cubed.
Minus 24t squared
Thank you.
plus 36.
All right. And what
T.
second are we interested in?
36t.
Oh, 3016. Oh, and they didn't give us a number to look at, did they?
No.
Yeah, there's no particular number to look at. That's okay. Let's find the critical points and the inflection points and see if we can put our graph together that way. So first, our velocity. Go ahead and calculate our velocity, Mario. Go ahead and do the derivative.
12t
The 12t what? Squared.
minus 3
Yeah.
t.
Ah. Okay, great. So there's our velocity. And they asked us, when does the velocity equal 0? That's nice. They just came right out and told us to set this equation
Equal to 0.
equal to 0. So I'm going to box it. That's my new equation I'm about to solve. You can do the quadratic formula on that, but what would be more convenient? Yeah, we can factor out at 12, right? This would be nice. 12 outside of t squared minus 4t plus 3. That's a wonderfully simple quadratic to factor. I'm going to divide off my 12 just to get rid of it. And how does t squared minus 4t plus 3 factor? 1 multiplies to make 3, that adds to make negative 4.
3 times 1.
Yeah, is it just 3 and 1? What kind of 3? What kind of 1? Yeah, both negative. All right, well, this is interesting. That tells us that when is the velocity equal to 0? When time is 3 and time is 1. Now, I'm going to start making a graph. And so I've got 1, 2, 3, 4, 1, 2, 3, 4. I know I have two flat spots at 1 and 3. Do I know where the flat spots are?
No.
I don't. All I know is that I've got a flat spot somewhere here, and I have a flat spot somewhere here. So how do I find the y-coordinate of my flat spot?
Okay.
Yeah, I have to plug it into my s function. So we don't have to show much work for this. You just have to write it down. So s of 3 is what? And s of 1 is what? That's going to tell us the y-coordinate of those flat spots. So just taking your calculator for
You plug it into the original.
you plug it, yes, you plug it into the original function. Well, that's crazy. Did anyone else get s of 3 is equal to 0?
Yes.
Okay, that hurts the brain just a little bit. There's a flat spot at the coordinate 3, 0. Remember how to interpret something like this. If it's a function of a number equals a number, that's input, output, that's a coordinate. So our first flat spot is at the coordinate 3, 0. There's a flat spot right there. There we go. There's a flat spot right there. So now we plug 1 into the function.
16.
I agree with you, 16. And again, input, output, that's a coordinate. So now we have a flat spot at the coordinate 116. So I come over here, I come up to 16, and there's another flat spot. This is kind of like like a fun workbook for children. How you turn the page and then you scratch off the outer layer, like with a coin or something, and it reveals a picture underneath. I guess that's like a lottery ticket. You scrape off the gray and then you see what's underneath. That's what's happening right now. We're slowly revealing a picture of what this graph looks like. We are the graphing calculator. We don't have a graphing calculator, so we are the graphing calculator. Okay, so now what? Are we done with that question?
Find the acceleration.
Where does the velocity equal 0? We just found it. Right. And we answered the question very specifically. We didn't just say the velocity was 0 at 1 and 3. Oh no. We said the velocity was 0 at the coordinate 116 and at the coordinate 30. So we answered the question as specifically as we could. Now, find the acceleration. So now we go ahead and proceed to find the acceleration function. I'm going to come all the way down here. So what's my acceleration function? Luis, what's the derivative of velocity?
Of that 12,
Yep.
times 24,
24t.
minus 48.
Yep. So there's my acceleration function. And remember, that's actually the second derivative. So now what do we do with this function? As a general rule, you take the derivative, set it equal to 0. That's your critical points. You take the derivative, set it equal to 0. That's your inflection points. So what do we do now? We set it equal to 0. And where previously 3 and 1 were our critical points, I should have labeled that earlier so you would have too, critical points. Now I take the second derivative and set that equal to 0, and that will tell us our inflection points. So we can probably do this one in our head, but it's 24t equals 48, and so t equals 2. That is my inflection point. And again, go ahead and immediately plug that into S. We want to know where that point is. We know it's at 2, but we want to know where that actual coordinate is. So S of 2, hopefully you still have that in your calculator, so you can just go back and plug 2 into it. I do. 2, 2, 2. Did anyone get 8?
Yes.
Yeah, so S of 2 is equal to 8. So now I can go to my graph, and 8 is easy. It's halfway to 16. And there's my point right here. And that's not a flat spot. That's my inflection point. That means we're changing concavity. And you can already start to imagine it, right? This is probably concave down right here. And then over here, this is probably concave up. We're just guessing. We don't really know yet. But theoretically, an inflection point changes from concave down to concave up. So what's one other point that we might want to know? What happens at time equals 0? Time equals 0 is a good thing to find, because that tells you your y coordinate. I'm sorry, your y-intercept. What if I plug 0 into this whole function? It's 0. Well, that's nice to know. S of 0 equals 0, therefore the coordinate 0, 0 is on my graph. And now we can really connect the dots. We have enough points here that we could really draw a nice picture of our graph. So what do? We start at 0, we go, that's all concave down. And then that's concave up. What's going to happen over here to the right? Could it ever come back down again?
Maybe.
If it did come back down again, wouldn't that mean there's another flat spot?
Yeah.
And did we solve for more than 2 flat spots?
No.
No. So it cannot come back down. Could it ever change concavity again? Could it ever switch from being concave up to start being concave down? That would imply another inflection point. Did we find a second inflection point? No. So what is this graph doing over here?
Just going up.
It just goes up. It just goes up and up and up and up forever. And we know that. Isn't that so cool? We know that. Because there are no other critical points and there are no other inflection points, so it continues to be concave up forever. Folks, I have goosebumps. I don't know about you, but using calculus alone, we just identified that whole graph without using a graphing calculator. 4x cubed minus 24x squared plus 36x. How did we do?
Good.
I mean, folks, that's amazing. Hold on, let me make this x look a little better. Whammo! Look at our graph. We should all be a little impressed. We really should be. We should all be a little impressed that we know what our graph looks like. We did a really nice job of finding that graph. All right. Well, that's it for that problem. I don't think there's anything else we could possibly say about it. We found the 2 critical points, found the inflection point. That's it. So let's try the next one, number 7. This is one of those fun problems that we tried before where we have to figure out which is which. So one of those graphs is the function, one of those graphs is the derivative, and one of those graphs is the second derivative. How would we possibly know which is which? Because at first glance you might think, oh geez, do I just have to try all of them? Maybe try that one, what's the derivative of that, what's that one? That sounds like it could be an overwhelming problem. But you're probably all already reading my note, my keep in mind. What is my keep in mind? Well, first, let's just take a guess about these graphs. What's the general equation for the green one? It's a parabola, so that's got to be x squared, right? So we definitely have one function that's x squared. What's the blue graph? The blue graph is this is a line. I mean, as far as we can tell, it's a line. So we also have a graph that's mx plus b. And then what is the green graph? That's probably a cubic. We've seen some cubics already. Cubics generally do something like that. So that can be a cubic. So really, what do we have so far? We have an x to the first, an x squared, and an x cubed. That's for sure we know those 3 graphs that we have up there. And the other thing we know is that as you take derivatives, the exponent decreases by 1 every single time. So what's the order of our f of x, and then our f prime of x, and then our f double prime of x? Which could be which? What has to be the original function?
Yeah.
Everyone agrees x cubed? Because that's the highest exponent. What happens if I take the derivative of the cubic?
No.
I would get some sort of x squared. And if I take the derivative of that, I would get some sort of linear function. Now, do I know what the coefficients are? I have no idea what the coefficients are. The coefficients, honestly, don't matter. The point is that as you take a derivative of x cubed, you get x squared. If you take the derivative of x squared, you get x. So what's the original function? The cubic, which is what color? Red. So the red one is, and just label it, just get in there and label, the red one is f of x. Gosh, I hope I someday don't actually write on this thing. That would be terrible. But yeah, the red one is your f of x. Which one is f prime? Yeah, the green one. Red. And then what, blue? Okay, here's a fun way of thinking about it, folks. If you take the derivative over and over and over, what do you do to a function? The first function went like that. When you take the derivative, it goes like that. When you take the derivative, it goes like that. Yes, absolutely, and I think that's what I said, right? It decreases the number of inflection points, and it straightens it out. Yeah, this is really interesting. Oh, and I think I even said it. It decreases the amount of wiggles. You'll notice my first graph had how many wiggles? 1, 2. Whereas the second one only had a single wiggle, and then this one had no wiggles. So the act of taking the derivative removes inflection points, and it removes wiggles. And so that's just something you can keep in mind.
So next to the 4th power, we have 3.
And x to the 4th power would theoretically have 1 wiggle, 2 wiggle, 3 wiggles. Yeah. Now that's just the maximum. An x to the 4th graph could just look like that. The exponent just tells you the maximum number. Yeah. But actually, folks, if we consider a wiggle to be a concavity, how many wiggles does x to the cubed have? At most. Only 2. And then how many wiggles does an x squared have? At most. 1. And how many wiggles does an x to the 1 have? 0. So the number of wiggles compared to the number on the exponent is what? you always have one less wiggle than you have the power on top, right? I know that's a weird way to say it, but it's true. All right. I just have a couple more problems here, 8, 10, 11, 12. Let's look at number 10. Number 10 is really in keeping with what we were just saying. Oh, and I'm not out of time now. Oh, I am almost out of time. Okay, well, let's in any case look at 10. But we can finish up the rest next time. So determine the signs of each of these. This is a great question. What is the sign of f of 2? And keep in mind, what are we talking about with the function? The function represents the
Y.
coordinate. The function is the y coordinate. So the y coordinate, is it positive or negative? And remember, we're looking at this point right here, f of 2.
Negative.
Yeah, the y coordinate is negative. What's the slope? Is the slope positive or negative? 0, actually. Yeah, the slope is actually 0. And what about the concavity? It's going from concave down to concave up. So the concavity right there is 0. Because it's an inflection point. It changes from positive to negative. I'm sorry, I probably misled you a little bit by just saying positive or negative. Some of the answers were 0. So here the sign of f of x, the y coordinate was negative because it's below the x-axis. The sign of the slope was 0 because it was flat. And the sign of the concavity was also 0 because it's an inflection point from concave down to concave up. So the y coordinate was negative, the slope was 0, and the concavity was 0. It's a good problem because it just makes us think conceptually about what these things mean. You're not really doing any calculations at all, are you? Okay, well, I obviously ran out of time, so we'll wrap these up next time. And what, today's Thursday? Yeah. So these won't be due on Tuesday because we're not done with them. So I'll extend the due date until the following week. All right? I have some papers to pass back, so please, I don't know if it's for everybody, but.
I just want to make sure I get these back to you.
Where's the Dom today? Oh, wait, Dom. Okay, well, that's it. Thank you.
Question on just one of the questions we're putting in 3 to the
3 times e to the p. Yeah, so here's how it's. Look at the ln button, right above the ln button. Yeah. Yeah, you just took that. Second ln.
Yeah.
Yeah, and then
then
3.
Like I